Okay, here we go to the next part of the problem. This one involves some calculations. We've got in an experiment 40 mLs of 0.25 molar, that's our hypochlorous acid, is placed in a flask. We put it into a flask, then we get a burette, and we add some sodium hydroxide to it that we had in that previous equation. We add 14 mLs, and here we've got a concentration 0.435 molar sodium hydroxide. Calculate the amount of sodium hydroxide in the 14 mLs of 0.435 molar sodium hydroxide. Oh, this is a pretty straightforward problem. Very often buried in FRQs, there'll be a simple question like this where you can do something that you know pretty easily and just quickly fire out an answer and get a quick point. So don't give up on an FRQ if you don't know the first couple of things. Buried in it will be something that you can easily do. And of course, you know this. Concentration times volume will end up giving you moles, the amount. This is just like we know that if you take grams and divide by molar mass, we get the amount. This is one of the equations that by now should be second nature to you. So let's do the calculation. I'm going to take and look here. I'm dealing with sodium hydroxide, so 14 mLs of 0.435 molar. Of course, we know that 0.435 molar means moles per liter. I mean, that's an automatic again. This M's an abbreviation. Moles per liter. We have 6.02 times 10 to the 23 of these hydroxide polyatomic ions times 0.435 in a liter. Quite a few little hydroxides floating around. And we multiply that times the volume. Now you say, wait a second, you've got liters here and milliliters here. Fine. That's great. I can do that. I can cancel out the liters and liters, and I get M moles millis. So I could just keep that unit just like this. There we go. 6.09 millimoles of hydroxide. The graders know what M stands for as a prefix. They know that stands for times 10 to the negative 3. Now, if you want, you can write times 10 to the negative 3. That's a pain in the neck. And you should be very comfortable in using millimoles. Don't forget your graders who grade AP exams. They're chemistry teachers who know what they're doing. In fact, they might even prefer the millimoles. Seeing this times 10 to the 3 over and over and over again will be boring. So, okay, we got one quick point. If you didn't have time to do an entire problem, you could have easily done this problem with your basic knowledge that you got back in chapter 4. Next, calculate the amount in moles or millimoles of the hypochlorite ion and our acid in the flask after the NaOH has been added. Okay, this is a tougher problem. This one's probably going to be worth 2 points. One of the points will be finding out how much hypochlorous acid was put in there, which is just like this concentration times volume. And we can just do that pretty quickly. Same basic idea, 0.25 moles per liter times our 40 mLs of volume. And you probably won't need a calculator for this one because that's 0.25 is a quarter times 40, 10 millimoles of HOCl. That was in the flask, but not for long because the sodium hydroxide reacted with it. Go back and look and you'll see that equation that the two react with one another. So now is time for an ice chart. Oh, I love ice charts. Now we're going to keep the amounts in millimoles because I don't want to type in times 10 to all the time. This is going to make things easier, and this is why I love millimoles. Here's our reaction. We've got our 10 millimoles of HOCl that we had in the flask. We dump in 6.09 millimoles of hydroxide ion. Arrow. Completely react to make water and our hypochlorite that's so happy as bleach. And here we go. Initially, that's what we start with. Arrow. It's going to change. Don't have to worry about an equilibrium here in terms of a Ks or anything else. This is 100%. And obviously, this 6.09 is going to react completely. There's 10 here, more than we need. We haven't reached the end point or the equimolar part. So we end up making hypochlorite ion. In fact, that's really how they get the hypochlorite in that bleach because the sodium hypochlorite is just so unstable. And here's what we have at the end, which will make an equilibrium, and I'll deal with equilibrium later. This answers our question. Calculate the amount of HOCl. Here's HOCl. Afterwards, here it is, 3.91 left. We have a little bit of this acid left, but our hydroxide's gone. It's completely gone. We didn't have enough of it. We didn't have any excess. But it went for good cause because it made some of our hypochlorite. Our second part of the answer, we're set. We got this problem taken care of. Titration is an important part of AP chemistry and chemistry in general. It's an analytic method that's used constantly to find the concentrations of substances that you're interested in or the amounts that's there. It's a great way of measuring things. And you start off with what we refer to as the analyte, whatever you are measuring and want to find out about. And you measure it out carefully in terms of volume. You can use a pipette that will give you an accurate volume, in this case of an acid solution, or if you are dissolving a solid, you'd end up weighing it. Once you dissolve your solution or you've put it into your flask that you're going to do the measurement or the experiment in, you often have to add an indicator, a few drops, as little as possible, to color the solution. Sometimes the solutions themselves will change color as they go from one substance to another. Then you don't need an indicator. Or you can use a pH probe if you're doing a reaction that has acid and base. Then you get your other item, a burette that has in it a solution that will react with your analyte. And you know about this solution. This is one that you make up yourself, that you know the exact concentration and composition of. In fact, that's why you've got this burette, because you're going to take something you know and find out about what you don't know. Titrant, you know about your analyte, you're analyzing it. That's what you are going to discover by its reaction, having one substance react with another and measuring the amounts. So you start off with an initial reading of this burette. It's very difficult sometimes to start at zero, so very often you'll just pour some in and get this initial reading. Then you pour in titrant and you watch the reaction and you mix and you let these two react with one another. And you keep observing it until you see the change that indicates that the analyte has completely reacted. In the case of an indicator, if it has a pKa of a pH that you want for this final reaction, that's when you stop things. Or if you've got a substance that changes color when it's used up, that color is missing, then you end up stopping. But there is some indication here, maybe even your pH probe will help you, that the analyte has been completely used up, and that's your final reading. Now that means that you're going to have a data sheet that has a initial reading that you wrote down very carefully and a final reading that you ended up taking down very carefully. This is out of an AP exam. Let's see if you can read it accurately. Now, one of the things about a burette is that they read upside down because they're designed to pour things out. So you start at zero. And notice on this AP question, they didn't put a zero here. They presume that you know that a burette pours out. This reading starts with zero and then moves down to this volume. That volume is going to be 0.65 mLs, and you're expected to estimate between the lines. So you have a 0.1, 0.2, and here's our 0.5, 0.6, 0.7, and that bottom of the meniscus is at the 0.65 level. Then you have your final reading here, and again, this one is helpful because you start at 21 and you go down to 22. So you have 21, and that line is right on the money, it looks like, and I would estimate that as being 21.3. On the AP exam, you could have a little bit of leeway on this hundredth of an ml. So if you said 0.66 or 0.63 or 0.31, you were given full credit for it. But then to find out how much titrant that you use to react with our analyte, you're going to have to do a subtraction. And again, with subtractions, we know things pretty well to the hundredth of an ml, so we'd carry our answer out to a hundredth of an ml, and that would give you the full point. Very often on a subtraction like this, they will mark it wrong if you don't include the hundredths of an ml and have the right number of significant figures for this. This is a classic method of finding the amounts and concentrations by using a chemical reaction. This is the beginning of analytic chemistry. In fact, here's the first burette that was used, and it was developed by a pharmacist, Friedrich Mohr, and he wrote the book on analytic chemistry, and he has detailed this method of titration. And this book explains this classic method that's still used today. So we've been doing titrations for 150 years. Now, these burettes haven't changed that much. They just have a Teflon valve here rather than these pinch claps. In fact, I used to use a pinch clamp, but this is referred to as a Mohr pipette when I first started teaching. Well, let's go to Wits University, where we can see how a titration is performed in a typical lab. Here we've got two flasks. One has our unknown acid that we have the approximate concentration of. We're going to titrate it using a standardized sodium hydroxide solution that we know is 0.1088 molar, 4 significant digits. It's our acid that we don't know about, only 1 sig fig, so we'll need a titration to figure that out. And we'll start off by taking that acid with approximately 0.1 molar and putting it in a flask. We'll use a volumetric pipette, which is very accurate. We can get 20.00 mLs of that unknown acid into a flask. Then we'll add some indicator. In this case, they've added some phenolphthalein. So we're starting off with our analyte, our HCl for the unknown concentration. We have 20.00 mLs of it, and we're ready to add sodium hydroxide. We'll get the initial reading here very accurately. Then we'll add the titrant. We gradually add until finally we get to the point where we know all of the acid has been reacted because of the change in color by the indicator, this pretty pink that you get with phenolphthalein. Record the data, and then we can do our calculation. Here's the data that was recorded. We had a volume of base that we averaged to be 22.09. We have its concentration, 0.1088 molar. And then we can divide by the volume of the acid that we had in the flask, 20.00 mLs. And now we know the exact concentration of that acid. We've determined its concentration to 4 significant digits. That's what a titration can do. Burettes have been the standard for determining volumes in titrations for over 150 years. Now, however, there are some new devices that will relegate that beautiful burette to a museum. Cue the music for the auto titrators.
Mettler-Toledo's Titration Excellence line instruments are tailored exactly for user workflows. Smart Sample uses RFID technology to optimize workflow efficiency. At the balance, the sample data and weight are saved onto the RFID chip attached to the sample beaker. Together with the sample, the data is transferred to the Excellence titrator, where it is read and saved. Therefore, Smart Sample prevents transcription and sample mix-up errors. Thanks to the one-click usability concept, analyses are executed with just one simple keystroke. Status light helps to increase efficiency by visual signaling. The operator can stay in touch with the titrator from anywhere in the lab.
So that's our digital titration. Note, we didn't have to read any meniscus, we didn't look at a burette, there's no scale. In fact, even the data was recorded electronically. With this volume of acid and this volume of base that we get from the midpoint of the pH curve, we can calculate the concentration of this acid, just like we did before, except with even greater accuracy.